Hi.
Awesome, thank you. Okay, so we have Oliver, so take it away with the FLO. Thanks.
Okay, cool. Yeah, what we're going to start with is we're going to start with a system of n qubits. So we have a bunch of qubits. I'm going to arrange them in a line like this. There's n of them. N of them. Oh my gosh. N of them. There we go. And we're going to try and use these to simulate a fermionic system in a natural way. Okay, here n is 4, but whatever, pretend there's n of them. So okay, how do we do this? Well, a fermion can either, each of these qubits is basically going to be a kind of a position in space. So we're going to have n points in space where fermions can be. And okay, if you look at the Wikipedia page of fermions, they obey the Pauli exclusion principle. So essentially only one fermion can be in a place at any time, which is why we're allowed to use qubits. So what we're going to say is that for each qubit, essentially that qubit is going to be in the state 0 if there's no fermion there. All right, fermion there. And it's going to be in the state 1 if there's a fermion there. Okay. And then Pauli exclusion principle basically says I can do this with qubits. I don't have to allow more and more higher spins because they can only be either 0 or 1 fermion. Okay, so the way we kind of do this is we create some creation annihilation operators to make and destroy fermions on sites. So I should say that there's going to be a whole bunch of fermions flying around on this system, but because of Pauli exclusion, there can only be up to n of them. But anywhere between 0 and n fermions is allowed, and including superpositions of different numbers of fermions also allowed. That's fine. So what does a creation operator look like? Well, it has to, I'm just going to use this notation A dagger for now. A dagger has to take 0 to 1. And because there can only be one fermion on a site, A dagger squared has to equal 0, because we're not allowed to create two fermions one after the other. In particular, this means A dagger applied to 0 is going to be A dagger applied to the vacuum state 0 is going to be the actual number 0, the vector with 0 length. Okay. And okay, I use this notation A dagger without explaining why, but essentially creating a fermion is going to be the same as annihilating a fermion kind of back in time, right? There's some sort of time symmetry. So A has to do kind of the same thing. A1 has to be 0, and A0 has to be the thing 0, because you can't annihilate something twice. Okay. Fine. And these are going to be defined for each position in our kind of discrete space, our n point space, or alternatively, they're going to be defined for each qubit. So, okay, we can almost just see how to write one of these things down, right? We can see that A dagger has to look something like 0, 0, 1, 0, just in the normal basis, and A has to equal something like 0, 1, 0, 0. So these map 0 to 1 and 1 to 0, like I said, for each qubit. Sadly, there is another, well, not sadly, there is another important property of fermions that we want. Namely, they do something really, really weird, which is if you have a system of identical fermions, I swap a pair of fermions, my overall state gets a minus sign. And I have personally no intuition as to how this could possibly be true. This is a completely insane fact to me. I mean, it is just a fact essentially for here. If I swap two fermions, I have to get a minus sign. So okay, it's fairly easy to arrange that to be true. What I do, so here I'm just going to write this as x plus x minus iz minus iy over 2, and this is x plus iy over 2 written in terms of Pauli operators. And I should, I guess, define this for each qubit. So this is true just for each qubit. I define one of these things. So just a little subscript. So I want these things to anti-commute. And okay, since I wrote the A's and A daggers in terms of parity X and parity Y, it's fairly easy to see how to make them anti-commute. What you do is you just stick a string of Z's in front of them, right? So actually what you do is you don't define this. This is wrong. What you instead do is you define, in order to make the commutation relations work correctly, or to make the spin statistics theorem work, to make the swapping give you a minus sign, what you do is you write AJ dagger is a product from I is 1, say I is 1 to J minus 1, ZJ, X plus J plus I. Which am I doing? Minus IYJ over 2. And the same will be true for a J without the dagger. So this is a creation operator. And you can basically see what happens if two creation operators hit each other and multiply together. Like I dagger, a J dagger. The one with the the one for which the index is higher, one of the Z's from the tail of that, one of the Z's at the start of that will hit the X and the Y operators here, and you get a minus sign. So you essentially get the anti-commutation relation correctly. And you can kind of summarize all the commutation relations that we want in the following way. We want AI, AJ to anti-commute for all I and J. We want AI dagger, AJ dagger to anti-commute for all I and J. And we want AI, AJ dagger, yeah, to equal delta IJ against J. Is that correct? Yeah, that way around. Okay, and you can just see that the operators I defined in terms of the values obey these so-called canonical anti-commutation relations. And these are really the relations that we want for fermionic creation and annihilation operators. And you can kind of just okay, these kind of come into nowhere, but let's say a reasonable way to think about this is to say that I wanted these relations because I know that fermions obey these relations. And then I just kind of wrote down these operators here, these AJs and ADAGs to make these relations be true. Basically because I know that these are true already from physics. Okay. And this essentially this trick of starting with parities and starting with parity X's and Y's and sticking a kind of tail of Z's on them like I did here, in order to make the anti-commutation relations work correctly, is known as the Reardon-Smith transformation. Right. I guess actually, let's say this thing is the Reardon-Smith transformation. It's this mapping from these parity operators into creation and annihilation operators. We call it Reardon-Smith transformation. Okay. So we have these creation and annihilation operators. They turn out to be a little bit annoying to work with in general. So actually we're going to make a new set of operators, which go by the kind of slightly grand name of Majorana fermion operators. Majorana fermion operators.
Oliver, I have a small question on
Sure.
the
I'm going very fast deliberately, so I expect questions. But yeah, sure.
Okay. On the AJ dagger expression,
Yep.
like the correct one. So on the left, you have a product of essentially everything that's not J, because here you say I going from 1 to J minus 1.
Yes.
But in general, it's going to be everything that's not J, is it?
No, so say if J is 3, then this is something like Z1, Z2, and then X 3 minus I y3 over 2. But then we don't have any z's on like 4, 5, 6, 7, whatever, right?
Okay.
Right,
Cool.
it's essentially to the left. And there's some kind of asymmetry in how we define things.
I see.
But essentially, yeah, you need to have a fixed starting point, which for me, I guess, would be this this first guy here is going to be j is 1. And then you get z's between 1 and your current position, but not after that. Yeah,
Okay.
that's important.
So the
'Cause if I had to-
algebra that they obey, you know, the stuff in the box
Mhm.
is somehow not asymmetric, right? It doesn't
Yeah,
see
that's
this.
true.
I see.
The
Yeah, the algebra is
representation
very
is, right?
symmetric. Pardon?
Yeah, just the representation is maybe
Yeah,
asymmetric.
just if you want to write these things as in terms of qubit operators, as I do here, then you get something slightly asymmetric. But you know, it's not the end of the world.
Yeah, so then there are also the Bravi-Kitaev transformations, Varun, where you do it on graphs with parity checks.
Okay. Thanks.
But I think what Oliver shows here is kind of the canonical would be seen probably as canonical.
Yeah, this is kind of standard. Yeah, it is a bit ugly, especially because for what I'm going to say later, it's actually completely fine and allowed to have these particles arranged on a ring like this, right? And then your starting point is completely arbitrary. But you just have to essentially break the symmetry of the ring and assign someone as a starting point and be like, okay, I'm counting from here, and yeah, break the symmetry somehow. But yeah.
Thanks.
Yeah, so it is asymmetric, this definition, but it works. So whatever. Okay. So as I said, these guys are kind of annoying to work with, these A's and A daggers, essentially because there's 3 different anti-commutation relations here. And you know, 3 is a very big number. I can't be bothered to think about 3. Do you know? Sorry, I've just seen the thing in the chat.
And that's for later, just a note for others.
Okay, sure.
I didn't want to interrupt. Because
yeah, I
you
don't know this thing at all. Sorry.
Yeah, because you mentioned this this antisymmetry, and there are ideas how to actually measure it blindly in an experiment.
Yeah.
So, but actually protocols that are sensitive to the phase are not so obvious. But with quantum control by now, I think people can try to do it, which is for me interesting because often we are not sensitive to this phase. So that's why I mentioned it. But
yeah, so that I don't know the details, but I think you don't even, well, there's this result called the spin statistics theorem, right? That basically says if you're a fermion, then you are antisymmetric by the result of the theorem under the correct assumptions. So then if you can kind of treat like measurement of being a fermion.
So
having half inches.
But that is assuming structure of the theory.
Yeah. I think there's some assumptions that go into this.
Well, this paper by Philippe Haukerus and Michele, I think. It's more encoding this kind of information into an observable. So it's a little bit like you could learn it from the data. If you have a fermion, it will respond differently to the protocol than a boson. So because you could, for example, have different isotopes of the same ion, and if you don't distinguish them by some mass ratio, and then infer that it should be a fermion, then you could just move them around and acquire a phase, for example. I think that's roughly the physical idea. Okay. No, so yeah. For me, this thing where if you swap 2 identical fermions, you get a minus sign is one of the weirdest things that I was taught in my undergrad physics. Like, it doesn't make any sense to me at all. I just treat this as an empirical fact. Like, okay, I know this happens, but like this is very, very strange for me. But in some way, it is not very empirical because it's sort of the root of the theory, but it's not really something that you observe. So you're actually physically completely right empirically, because it's very hard to realize it. You will have to interfere and encode that onto observables. So that's like, I like that you say that it's weird, because in some way it's paradoxically very special, this phenomenon. Like we see the aftermath of it, but individually the protocol, I think it's still actually there was a talk in Singapore, right, at the resources talk about using this fermionic statistics, this minus sign, in order to detect something, right? Someone had a protocol that, That's another
sort of playing with the you know an exchange of the actual systems carrying the state versus like an exchange of the state kind of thing.
Yeah.
Yeah.
All right. Okay, I will continue. Okay, so these guys are annoying to work with because, you know, 3 relations is complicated. I can only really deal, in my head, I can only really deal with 1 relation at a time. 3 is too much. So if you just define these operators, and I have to get the indexing right, I guess. So I guess C2J minus 1 is going to be AJ minus AJ dagger with a minus I on it, and C2J is going to be AJ plus AJ dagger. These then, it turns out, if you start with these things, you can prove that the anti-commutation relation star above is exactly equivalent to the relation CI CJ is to delta IJ. It's only basically only one sort of relation, one kind of type of relation, which is a lot easier to deal with. So it's, yeah, we just use the Majorana operators. It's completely equivalent. Any expression in terms of Majoranas, you can rewrite in A's and vice versa, but these are easy to deal with because only one relation. And actually, if you look at, go back to my definition in terms of the Jordan-Wigner transformation of the A daggers and the A's, you get that this is something like a product from J is 1, sorry, a product from I is 1. I is 1 to J minus 1, Zi Yj, and this is the product from I is 1 to J minus 1. Oh, crap. Zi X J. Okay, so these are ways to work with. I just have Pauli strings, X and Y's. And actually, you can take these Majorana operators, these CJs, to be just a different generating set for the Pauli group on n qubits. That they're just, you know, writing out this group in a different way. And of course, you generate exactly the same like algebra of operators that you do out of the normal Paulis on n qubits. Everything's exactly the same. It's just these C's are a different like generating set for the Pauli group. Yeah. If you look at them for a little bit, you can prove that, you know, if I have any Pauli string, I can rewrite it as a string of C's and vice versa. Okay, so these are very important and going to be very useful. So I am gonna, how do I get any page? I don't know. Okay, so I'm gonna define now some actual like physics rather than just defining some operators. We're gonna allow some unitaries. We're gonna define a set of unitaries, okay, which I'm gonna call FLO unitaries. And these have 2 characterizations, or here they have 2 different characterizations. One is they're unitaries such that U, C, I, U dagger is a sort of canonical rotation. Some of a J, oops, IJ, CJ, where R is an orthogonal real 2n matrix. Okay. Orthogonal? Yep. Okay. The other equivalent characterization is that U is essentially unitary generated by a Hamiltonian which is quadratic in either the A's or the Majoranas or the C's. So U is EXP. This factor of a quarter doesn't do anything. It's kind of pointless, but it makes things neater. Sum over IJ, alpha IJ, CI, CJ, where this thing is a real 2n by 2n, and alpha transpose plus alpha is 0. So alpha is anti-symmetric or skew-symmetric. Okay, so the fact that these 2 characterizations are equivalent is due to Barbara Turhull and David DiVincenzo in a paper from about 2004.
I can give the exact reference if you like, but yeah, it's Toho, essentially. And okay, we can say actually slightly further that if you have these like equivalents, actually the R that you get on the special the orthogonal R you get is actually exactly exp of alpha here. So it's a kind of nice relation here. And we know that orthogonal matrices are kind of generated by antisymmetric ones when you exponentiate them. That's why the factor of a quarter is here to make this formula work. Okay, this is very nice. It turns out, very surprisingly, actually, will I say that? I'll say this later. Actually, I won't say anything surprising now. Okay, so you have these FLO unitaries, and I'm going to also define a set of what are called fermionic Gaussian states. Fermionic Gaussian states, which I guess you could also call realistically FLO states, which is anything you can make by applying U to an initial vacuum state, essentially where this guy is an FLO unitary. There's a few equivalent characterizations of all this stuff. A particularly useful characterization is due to, I think, Sergei Bravi came up with it first, which says if you take the Majorana fermion operators that I had before, okay, I don't actually want, I'm fairly sure this is Sergei Bravi invented this. But essentially, they say the result is if you take the Majorana operators I had before, and I define some operators, L is sum over J, Cj tensor Cj. So you just add up all of the Majorana's tensors with themselves. Then a state phi is fermionic Gaussian, is one of these fermionic Gaussian states. If and only if it's even, is even. And L phi tensor phi is 0. So this is also a useful characterization, which I think is due to Sergei Bravi.
Yeah, can confirm.
Yeah, Lagrangian representation of FLO or something it's called.
Correct.
I think.
Yeah.
Lagrangian representation. Okay, cool. This is useful.
And
okay.
and here just one comment, because for me it was very confusing in the paper because it's just stated and proven.
Mm-hmm.
And then Piotr Wikliński told me once to really view this tensor product as kind of arithmetical way of just checking something about the state. Mm-hmm. It's meant a little bit as a trick of like looking at that vector. Mm-hmm. And so it's more like a computation, a processing of this. It's not meant as a physical tensor product so much, as far as I understand.
Yeah, you want to check like some quadratic polynomial essentially is 0, right? And the way you do this is by
and so it's not attempting to create another physical system of fermions and then asking about some antisymmetry between them. It's not meant like this. It's just a characterization and if and only if criterion with this vanishing, as you said.
Yeah.
But
I
was confused.
Yeah. I should say, by the way, I didn't define what it means for a state to be even. So a state is even if you write it out in the computational basis as like sum over y in sort of bit strings 0, 1 to the n, a, y, y. If this decomposition has only non-zero weights on even bit strings, so bit strings with even numbers of ones in them, right? So for example, this thing is even 0, 0, 0, 0 plus 1, 1, 1, 0, 0 plus 0, 0, 1, 1 plus 1, 1, 1, 1. This is even, but like, 1, 1, 1, 0 is not even because it's got an odd number of ones in. Right? This is even, this is not even. Okay.
Okay. And I should say for completeness, actually, here there's a kind of exact symmetry between the even and odd subspaces. So you could also replace this word even here with the word odd, as long as you're only supported in one subspace, it's fine. But okay. Okay, so we have some fermionic Gaussian states and we have FLO unitaries. And then I guess for a kind of a complete nice subtheory, we should also have some measurements. So here my measurements are just going to be asking if there is or isn't a fermion in the jth kind of position. I'm not going to write that explicitly, but these are essentially the measurements that you can do. And obviously anything that you can get from those measurements by conjugating them with unitary is also fine. Okay, so now I'm going to change tack completely and talk about classical simulation. And I'm going to talk about some stuff that we know essentially from the, now before I talk about classical simulation, I want to emphasize something about the FLO unitaries. Okay, so I mentioned before that these C's are just another way of looking at this is just a generating set for the Pauli group essentially on n qubits, right? These C's. And there's an interesting contrast here between FLO unitaries, LO unitaries versus Cliffords. I apologize for my handwriting here. FLO unitaries versus Cliffords. All right. So if I just take these C operators as my kind of default generating set for the Pauli group, what a Clifford can do is given a sort of, what a Clifford does is it maps a string of Majoranas, a string of C operators to another string of C operators. So for example, you know, Clifford, you get something like C0, C1, dots, maps to C7, C3, whatever, right? You get different products. That should be the same. It maps essentially products of Majoranas to products of Majoranas. But what it does do is, what it won't do is map a product of Majoranas to a sum of Majoranas, right? It keeps kind of the rank the same. If you have a single product that will get mapped to a single product, you won't end up being mapped to a sum of two guys. On the other hand, what an FLO thing does an FLO unitary is it maps something like sum over J R I J C J gets mapped to sum over J S R, I guess, I J C J. So it maps sums of guys to sums of guys, but essentially you don't get any products, if this makes sense. So if you think about kind of the algebra generated by the Paulis, or the algebra generated by these C's, Clifford's map kind of weight one guys to weight one guys in terms of sum, and FLO guys map weight one guys to weight one guys in terms of products, right? If that makes sense. Like an FLO guy can't make you more complicated in terms of products, and a Clifford can't make you more complicated in terms of sums, if this makes sense. There's an interesting like duality, right? I don't know if this makes sense, but I think it's cool.
Does this property completely determine the Cliffords, or is it just like one property they have?
No, this completely determines the Cliffords, right? They're unitaries and they map Paulis to Paulis. This is everything. This is all you need for Cliffords, I think. Oh, actually for Cliffords, so to make it convenient for Cliffords, we also fix their phase, right? Because, you know, if C is a Clifford, then like each the I phi also maps Paulis to Paulis under conjugation, because the phi's cancel. But we want there to be a finite number of Cliffords, so yeah. We're up to, I think, up to this like global phases. This determines both the Cliffords and
I
the
guess I shouldn't use the word determine, more like define. Could you define the Cliffords through like this property? And
yeah, absolutely.
Okay.
Cool. Yeah, this completely defines the Cliffords. And it completely defines the FLO guys as well.
Okay, cool.
So one essentially maps products to products, and one maps sums to sums, and that's kind of cool. I have no like idea if this property is useful, but they're kind of doing like each one is kind of respecting a different aspect, a different operation in the algebra. Yeah.
Okay. This is kind of a side note that I think is cool. Okay, so where were we? We have fermionics, we have fermionic Gaussian states. Okay, so I want to do classical simulation very quickly. Classical simulation. Okay, so the idea of the kind of classical simulation algorithms we're going to be doing is we're going to have a quantum circuit that we want to implement. U1, C1. Okay, and I'm just gonna draw the one, U2. C2. I apologize for the terrible drawing. Dots, dots, dots. UN, I guess, over here. We're going to have an initial vacuum state here, 0. And we're going to do some measurements where we essentially just do a computational based measurement at the end. So, yeah. I'm not going to draw it. We're going to do a computational based measurement at the end. Okay, and what are these things? These U's individually are FLO unitaries. And these C's, UI, I for unitaries, CI are controlled phase gates. So CI is something like 1, 0. I'm not going to write the zeros actually. 1, 1, 1, e to the I, phi, 0, 0. In the just written as a matrix, the computational basis. Okay, so they're controlled phase gates to arbitrary phase. Why do we do this? Because circuits made out of U's and C's are universal for quantum computation. The U's are FLO, and we have a nice way of implementing the C's, which is due to this paper, which I will just send to you, I guess. Yeah. It's easier. Yeah. So we know how to implement the C's essentially by this paper that I sent you. Does this work? So, yeah. Okay. So how do we implement the C's by this paper? What you do is you take each C, you remove it. So okay, I'll just draw it. C equals something more complicated. Six. One, 2, 3, 4, 5, 6. U with then some post selection here. Okay, and then I should say explicitly that what comes into here here we have, I apologize again for the terrible drawing. This is initial or 0 state. Okay, and then these two guys, the top and the bottom guy, are whatever state you have coming in. So I apologize, it's slightly difficult to understand, but essentially what happens is rather than implementing C on the two wires you want to implement, the two qubits you want to implement, you bring in this ancilla system, which starts in all 0 vacuum state. You apply this U here, which is just some fermionic thing. Then you post select on 4 qubits, this M phi. And the overall effect is up to normalization. I should write some normalization. The overall effect is applying a CZ across these two input qubits. So I hope this makes sense. Great. And the key point here is that this U here is FLO.
This guy is FLO. This is just a vacuum state, so it's a fermionic Gaussian state in particular. It's a vacuum state. The only non-FLO thing that we have now is this M phi measurement, which we have to somehow implement. The way we implement this measurement is fairly simple. Yeah, I should say actually quickly before I go any further, does this diagram kind of make sense? Like, is this okay?
Yeah, I think so far so good. I will post the paper in the description later.
Yeah, sure. Okay, so the only thing that we do now is we have to work out how to apply this measurement to a fermionic Gaussian state. So this measurement, this is just a projector, I should say. We do post selection. So this state M phi that we project onto is given in their paper as something like 1/2 plus 1100 plus 0011 plus e to the I phi 1111. Okay, and it turns out that this M phi can be written as cos phi over 4.
Can you scroll up a little bit for us?
Oh yeah, sure.
Thank you.
It's okay. Plus I sine phi b of phi, where a phi, A and B are fermionic Gaussian states. Fermionic Gaussian. Okay, the overall effect of what we need to do is we need to project onto essentially A of phi and then also onto B of phi and add the answer up. This is not too difficult, right? Because A of phi and B.
Important, but I'm guessing the angles are the same in both terms.
Yeah. Yes, actually, I mean, okay, I don't want to give these explicitly, but perhaps it's easier just to do this. One sec. I don't think it matters so much, but if I share my screen here, I can just show you here somewhere. Yeah, okay. How do I zoom in here? There we go. Okay, so here we have M, A, and B, right? They're just some sums of whatever, zeros, ones with some faces on them. The actual, like, it doesn't really matter so much what they exactly are. Okay, if you want them, they're, yeah, 29, 30, and 31 are A, B, and M. Okay. Cool.
Cool.
Yeah. Okay. Can I go back to? Okay, I'll go back to showing here now. Yep. Okay. Am I showing my screen in the right place now? No, I am not.
And no, you're still on overleaf. Okay, now switched off.
Okay. I made this too complicated probably then.